The last topic for Notes 2 is actually not a very complicated one. It's called isotopes. And isotopes are atoms from the same element that have the same number of protons, but they have different number of neutrons. Okay, so we have two of the exact same element, but they have different number of neutrons. So here's an example of one that I can give you. A very common one that we'll study next year in biology is carbon. So we can use carbon isotopes to do like fossil records and things like that, determine how old something is. In this example, we've got two samples of carbon. They do differ just barely. Just taking a look at the symbol here, we have a number in the upper right and in the lower right. They both are 6 on both of these samples, and that is the atomic number. That's the number of protons in each sample of carbon, and the protons are represented by the red circles here. And so we have 6 here and we have 6 here. The 12 and the 14 represents not the number of neutrons but the total mass. Okay, so if you recall from earlier, that mass number is protons plus neutrons. So if I have 12 as my mass number on this sample and 6 of it is protons, that means the other 6 has to be the neutrons. And you can see in this picture the white marbles here, there's 6 of them, whereas over here we have 14 being the mass, 6 is protons. That means the other 8 have to be the neutrons, and if you count all of them, there are indeed 8 of those white marbles. So isotopes do exist where you can have a varying number of neutrons. A lot of times this happens with radioactive elements where you have more neutrons than the atom can hold, and you have neutrons firing off, and that's a type of radioactivity. That can be kind of dangerous. So it's really important to understand how much of each element exists in nature, and we basically take the average of all of the masses from those isotopes, and that's the number that we see on the periodic table. Okay, so I'll give you an example here. We've got carbon 12, carbon 14, and here's another example of that. We've got 3 different isotopes of hydrogen. So these are all hydrogen, and the way I know that is because they have 1 proton each. Okay, so this is a proton in the center, 1 proton here, 1 proton here. All 3 of them are hydrogen, except in some cases you can also attach a neutron to that proton. Out of all of the hydrogen that exists in the universe, like 99.999% of it, a lot of it is going to be this isotope right here. It's going to exist in this form on the far left, where it has 1 proton, no neutrons. However, there are cases where you can attach a neutron to hydrogen, and that is called deuterium. Okay, and over here you can actually have a version where you attach 2 neutrons to the hydrogen. So what does that mean? It's not really anything important for you, I guess, but that does mean that if you wanted to make water with deuterium, the 1 sample of water and that had deuterium and then 1 sample of water that had protium over here, this hydrogen, the deuterium would actually weigh more, even though they might have the exact same amount of water in terms of volume. So the deuterium does increase the mass of the hydrogen. Okay. The normal one on the periodic table appears right here because that's going to be the most abundant. Like I said earlier, 99.999% of all the hydrogen in this universe exists in this form right there. Okay? So here's an example. Let's say I have a sample of chlorine, and then I have like a dash and the number 37. That 37 is representing the mass. Okay? So if you have the name and then the 37, that's representing the mass. The protons, I just have to look that up on the periodic table. If I look at the periodic table and find chlorine, I notice chlorine is number 17 on the periodic table. That means it's got 17 protons. The number of neutrons, well, that's got to be 20 because 17 of this 37 is the protons, and the remainder has to be whatever neutrons you have left. So 37 minus the 17 protons leaves me with 20 neutrons. So it's the new mass minus the protons. And then finally electrons, 17, because the number of protons and the number of electrons typically is going to be the same. All right, let's say, for instance, I was able to gather all of the chlorine in the world and put it in one big room. All right, and let's say I was not dying from all the chlorine because chlorine is a very toxic gas, but let's say I was able to measure the mass of all the chlorine in the world. All right, and then I found that when I measured the mass, I was able to find two masses. I found some of the chlorine weighed 35 and some of the chlorine weighed 37. And when I did the percentages and I did the calculations, I found that 75.5% of all the chlorine in the world weighed 35. And the remainder of it, the 24.5%, weighed 37. Okay? And what I want to do is report a mass on the periodic table. I want to put a number on the periodic table that tells me what is the average mass of chlorine. Some people might want to say, we'll just put the most abundant one, right? If close to 76% of it is 35, just put that. But that would actually be incorrect because you have to account for the other isotope, right? And again, the difference in the weight is not the protons, it's the neutrons. So this chlorine has 2 more neutrons than this chlorine. All right, so how would I report that on the periodic table though? So on the periodic table, we see what's called the average atomic mass. So the atomic masses on the periodic table are an average of all the known isotopes of certain elements. So if we get to this point where we got to put the average of these two. Historically, what you would do for an average is you add them all up and you divide by the number of things. So in this case, we would do like a 35 plus 37. You divide it by, add those two up, divide it by 2, you get 36. However, that's not taking account to what's called the weighted average. Okay, that's if you're splitting it 50-50. But in this case, it's not 50-50. It's 75 to 25 roughly. So we got to take into account those percentages, and we get to something called a weighted average. And the way we would do that is take the mass, multiply it by its percentage in decimal form, and then add them all up. So mass times percentage, and you get a number, and then mass times percentage for the other one, and you get a number. So let's take this mass, I put a blue box around it, that goes right here, blue box. Then I take the percentage, red box around this one, and then I am going to convert it into a decimal form and put it here. If you don't know how to convert percentage into decimal form, this is how you do it. You take whatever your percentage is and you divide by 100. That's it. So you take 75.5, divide by 100, and that's what it is in decimal form. You multiply these two numbers. That's your next step. Multiply 35 by 0.755, and you get a number. Okay? Then you do the other side. You do 37. So here in this purple box, 37 goes right here. And then 24.5 in green goes right there. Again, divide by 100 to get in decimal form. Multiply it out. You get another number. Okay? You take those two numbers and you add them all up. So the periodic table mass that you see is 35.5. And that's actually what you do see on the periodic table. That's called the weighted average for that element. So to review, mass times percentage, and then add them all up. However, you can have more than 2 isotopes. You can have 3 isotopes, sometimes even more. So you have to do the weighted average for all of them. If you had 3, you'd have to do mass times percentage, total 3 times, and then add those 3 numbers up. Okay? So here's practice problem number 6. Number 6 says there's a new element, X, and it is found with 2 possible isotopes, X5 and X6. If X5 has an abundance of 80% and X6 has an abundance of 20%, what is the atomic mass that would be shown on the periodic table? So the way you would do this is you have to understand the symbol and the number associated next to it. So we have to understand that X-5 has a mass of 5. So whenever you see a dash like this and then a number, that means what that mass is. So X5 has a mass of 5 and X6 has a mass of 6. Okay? Now take those abundances and multiply them by the mass. So 5 times 0.8, because it's 80% from X5, and that gives me 4. And then 6 times 20%, or 0.2, gives me 1.2. Mass times percentage, and then finally when you do all of them, you add up all the numbers. So 4 plus 1.2 gives me 5.2. And so that's what you would put on the periodic table, is that the average mass is 5.2. So there you have it. That's the end of Notes 2. Notes 2 had a lot of different topics that we talked about. The big ones being, of course, electron configuration and isotopes. For the remainder of the time, what I would like for you to do is in your notes, take a look at practice problems 7 through 9. There's a lot of it. I'm not going to make a video based off of it, but I will be posting the key to this. So if you want to take a look at Canvas, the key will be posted and you can compare your answers to the key's answers, making sure you're getting the right numbers. So go ahead and work on that now.